So we're back to the Whirlpool map. This video is just going to illustrate that I can traverse the sides of A, B, C on a counterclockwise manner, producing zero, starting from zero from a chosen zero. I'm also showing the circumcircle of ABC, but that's immaterial. So if I start from zero, I can produce a point 1 by computing the centroid of triangle starting, with a starting side AB and an apex at this chosen point 0. The centroid of this triangle is going to give me point 1, right? So now I can do, to get point 2, I'm going to use point 1 as the apex of the next triangle formed by the side BC in counterclockwise manner with 1. That gives me 2 over here. And to get 3, likewise, let's just finish this iteration. So 3, I started with AB, then I went to BC, now I'm going to go to CA. So I'm going to get a triangle with the side CA and apex on the second point, the second computed centroid, and that gives me point 3. And I keep iterating this in counterclockwise manner. I'm calling this the Whirlpool map, and I end up getting this red path, okay? Now, the red path will terminate, will have a limit cycle represented by these 3 round dots here, okay? So this whirlpool is actually converging to a final triangle. And we said in the previous video, the ratio of areas between ABC and the terminal red triangle is as magical 13. And we can show this algebraically. We thought this was a pretty interesting remark, okay? Now what I'm showing on this video as well, and by the way, I can change, right? I can change my triangle and that area ratio doesn't change. 13 is always the same. Right? Now let's explain what the green path means. The green path means we're doing the whirlpool but in clockwise manner. So we'll start, for example, with side AC, then we're going to go to side CB, BA, and so forth and so on. So to get point 1, what we do is I get side AC, and then I get my starting location 0, and close this triangle. The centroid of this triangle, using side AC and this chosen point A, is point 1 prime. So now I'm like traversing the sides of the triangle in clockwise manner. If I move my starting location 0, you can see that that triangle moves and its centroid 1 prime moves as well. Now let's see how we get the second point in the series 2 prime. I started with side AC, so now I'm going to move forward to side CB. And how do I do this? I take side CB, and for its apex, I take the last computed centroid, which is 1 prime, and that gives me 2 prime. Likewise, to get 3 prime, I'm going to get the next side, A. So I'm going to get side AB and combine it with the last computed centroid, which is 2 prime. The centroid of this brown triangle is 3 prime. And so forth and so on in clockwise manner. Okay? Good. So now I get these 2 paths, and interestingly, each one of them has a different terminal triangle. So the counterclockwise path gives me these 3 red dots as a terminal triangle. And, oh, this thing is wrong. Let me just change the symbol here. Yeah, it would be this one here. Okay, and let me save that. And the green clockwise path going from this chosen 0 star to 1 prime, 2 prime, 3 prime, 4, so forth and so on, ad infinitum, right, is going to give me these 3 green dots here. Let's call this the terminal triangle generated by the clockwise whirlpool map, whereas the red triangle is generated by the counterclockwise. Now, interestingly, and I think this is a trivial thing to prove via an affine argument, we're just going to go over that in a second, but the 6 vertices of the 2 terminal triangles lie on this ellipse. Now, why is that? This one has a pretty easy argument. And by the way, the ratio of both areas is 13. Both the counterclockwise and clockwise terminal triangle, the ratio of ABC to their areas is 13, although these 2 triangles, whose vertices lie on an ellipse, are different. Okay? Now, one way to explain this is to realize that ABC is an affine image. So there's an affine preimage, if you will, of an equilateral triangle. Okay, so this equilateral triangle, ABC, shown here, you'll produce by symmetry, and this can be shown algebraically as well, two terminal triangles which are uh, centered on, the centroid of ABC, and are also equilateral. So you see here these three red dots here. If you ignore that 3 there, right? That 3 is something else. But if you look at these 3 red dots here, this is the terminal triangle for the counterclockwise iteration. Its centroid coincides with the centroid of ABC. And for the clockwise iteration, 1 prime, 2 prime, 3 prime, and so on, you end up with these 3 green dots, a different but also equilateral triangle, and obviously, because of symmetry and all of them share the same centroid with each other, their vertices are going to lie on a circle, right? So a corollary of that is that if I'm not working with equilateral version, you can always think of this as the image under an affine of the equilateral. So area ratios that you measure in the equilateral case, which are going to be 13, and that can be shown algebraically, are going to be preserved under this affine transformation, right? And affines also preserve conics, so the 6 vertices are going to have to lie on a conic. Okay, so I just wanted to introduce this idea of 2 distinct. Okay, another property is that because the centroid is invariant under the affine group, the centroid of both green and red terminal triangles is also going to coincide with the centroid of ABC. Okay, we have worked out some of this algebra, and one interesting thing that we found out regarding these 2 terminal triangles on the equilateral case is that they are rotated copies of one another at an angle theta such that the cosine of theta is 11/13. So this angular rotation here between the 2 terminal triangles is I think of approximately 32 degrees, and the cosine of that angle is 11/13. So that's pretty interesting. Okay, so I'll see you on the next video. There's quite a bit that we want to cover still. There's the n equals 4 case, n equals 5, n equals 6, and a pattern that we have discovered on higher ends. But n equals 4 itself is pretty interesting. We're going to do this on the next video. See you there.